So repeating the same kind of process for all of our other units. Now that we have a handle on the function, we're going to talk about solving equations and inequalities involving these rational functions. So when we're dealing with equations, we're going to run into a little bit of issues because we have this variable in the denominator. So when we go about trying to solve any type of equations really from this point onward, you want to make sure you're checking your solutions. And what I mean by that is not necessarily checking that they work, but more so checking that it makes sense in the context of the problem. So for us, the very first thing we need to do anytime we start one of these rational equations is we have to find all of our issue numbers. I like calling them problematic numbers. So basically, what is the domain of this expression that you're given? What values cause you the denominator to equal to 0? Because I know we cannot equal these numbers. Afterwards, we don't like these fractions, so we're going to go ahead and wipe them by multiplying through by the least common denominator. And in doing so, you're going to create either a linear or a quadratic equation that you then can solve. So you're going to find solutions that work for this resulting equation, but then you have to go back and check, were any of these one of our problematic numbers? So really the best thing we can do for all of these is just a ton of examples. So we're going to solve quite a few rational equations. So right off the get-go, when I look at this expression, I have x and I have 7x in my denominator. So without doing any work, I immediately know that my problematic x value is 0. So in the end, if I find out x equals 0, I know that is not a solution because that is an issue up here. Okay. What I want to do now is I want to get rid of these two fractions simultaneously without actually changing my equation. So if you need to look up a video on the least common denominator, there are tons of them out there, but this is something we did in intermediate algebra. So I need to definitely multiply through by x because I need to get rid of the x here in the denominator and the x here in the denominator. But I also am left with that 7, so really our least common denominator is 7x. So really I'm going to take this entire equation and I'm going to multiply it by 7x. That is the least common denominator of every fraction we have. So I'm going to add in extra steps than you necessarily need. If you feel comfortable just going ahead and canceling stuff, feel free. But I'm really taking every single term and I'm multiplying it by 7x, including the thing that wasn't a fraction. Okay. Now from here, I can start canceling stuff out. So in our first piece, the x's are going to cancel. And then in our last expression, the 7x completely cancels. So what we're left with on the first piece is 2 times 7. This middle piece becomes minus 14x. And the right-hand side is 12. So we've got a much nicer equation to work with. This is 14 minus 14x equals 12. And then we go about solving by x just by subtracting 14. And this gives us negative 14x is negative 2. And then one final step, we go ahead and divide both sides by negative 14. So this gives us x is equal to 2 over 14, and then that does reduce further. They're both divisible by 2, so we get 1 over 7. Okay. So we're always going to get some kind of solution here, but now I need to go back and see, was this a problematic number? And thankfully it's not, so this is the solution to our equation. So again, I don't have to plug it into my equation. I'm just checking, does it actually work for this particular problem? It's not an issue, so I'm good. This one works out. So let's try another example here. We've got quite a few fractions. Problem with this is I can't immediately tell you what my problematic number is. I also can't tell you what the least common denominator is. So what I'm going to do is I'm going to factor these denominators completely. So from this bottom one, we can take a 4 out. And that leaves us with x minus 3. And then in the second fraction, I can take a 2 out of both of those numbers. It leaves us with x minus 3. And then on the right-hand side, both of them have an x in common. So that leaves us with an x and an x minus 3. So now I immediately can spot out the issues from the first piece, the second piece, and the third piece. We see 3 as a problematic number. But then also we have an x in the denominator. So we also know that x cannot equal 0. So I have 2 problematic numbers. Now I want to wipe these fractions by multiplying through by the least common denominator. So looking at all 3 fractions, we definitely need to multiply by x to get rid of the x here. We also need to multiply by x minus 3 because every single fraction has that factor. And then I also have these constants 4 and 2. So the number that I can multiply by to get rid of both of those numbers is 4. Technically, you could multiply by 8 because that would wipe the 4 and the 2. You could multiply even by 16, but the smallest number that works for us is 4. Okay. So I want to take this entire equation and I want to multiply it by this least common denominator. So again, if you feel content just canceling stuff out, you can skip this next step, but I'm going to go ahead and write every single individual piece by the multiplied by the least common denominator. So we have our LCD times 1 over 4 times x minus 3. Then we have minus this fraction times our LCD. You can put this out front, doesn't really make a difference where. And then we have the right-hand side times the least common denominator. Okay. So in our first fraction, the 4 cancels completely, and the x minus 3 cancels. So we're really left with 1 times x. Okay. We got minus in the middle. The x minus 3's cancel, and then I've got 4 divided by 2. So it leaves us with a 2. So we really get minus 2 times x. And then on the right-hand side, the x's cancel, the x minus 3's cancel. We're just left with 4 times 1, which gives us 4. Okay. So really this is x minus 2x is equal to 4, which is just negative x equals 4. So moving that minus sign to the other side gives us x equals 4. Okay. And now again, I've got to go back and check. X equals 4 was not an issue, or negative 4 was not an issue number. So this is the solution to our equation. So I know every example we've done so far has had just a linear one. The last one, unfortunately, is going to be a linear one as well. But it's very possible you could end up with a quadratic equation that you have to solve. And this one's going to be a little bit more complicated too, because you're going to see something funky happens in the end. So this one is fully factored for us. So right off the get-go, we pick out our problematic values. So x cannot equal 4 from these 2 fractions. And then also we can't plug in 0 because we have an x in the bottom here. So these are our 2 issues. For here, our least common denominator is going to be x times x minus 4, because that's the only 2 different factors we see. So I want to take this entire equation and multiply it by x and x minus 4. So we've got our first fraction multiplied by x and x minus 4. Second fraction multiplied by the same thing. And then third and final fraction multiplied by x and x minus 4. So in the first piece, the x minus 4's are what cancel. That leaves us with 2 and x. In the second piece, the x's cancel. So that leaves us with minus 5 and x minus 4. And then nicely on this last one, both of those factors cancel. So it just leaves us with 8. So now we go about solving this, and it is linear like I said it was going to be. So we distribute that minus 5, and that gives us minus 5x plus 20 equals 8. 2x minus 5x is negative 3x, plus 20 equals 8. And then we go ahead and subtract 20, and that leaves us with negative 3x equals negative 12. And then one final step, we divide both sides by negative 3, and that leaves us with x equaling positive 4. So here, again, this is where checking is really, really, really important, because if I go and try to plug 4, I run into problems. That is one of our issue numbers. So really, this is not a solution. Yes, it solved the resulting equation, but it doesn't actually solve the original equation that we were given. So there are actually no solutions to this problem. Okay. Extraneous solutions are really likely to happen from this point onwards because we're dealing with more complicated expressions. So I know you're probably not in a habit of checking your answers, but you need to here, right? So let's try some rational inequalities now, kind of take it up another notch. So remember, when you're dealing with an inequality, you're trying to find the intervals that satisfy that given expression. The one thing that's really tempting here is you want to wipe those fractions by multiplying through by the denominator. You can't do that with an inequality. And the reason we can't multiply by variables is really based on our core kind of rule when we multiply or divide by negative numbers. So remember, anytime you multiply or divide an inequality by a negative number, it flips the sign. The issue is when you have a variable, you don't know what sign that is. You don't know if x is positive. You don't know x is negative. So if I have something like 1 over x is greater than or equal to 3, I can't just multiply these by x because I don't know what happens to the sign in the middle. So this is really ambiguous for us. We want to avoid doing that. So instead, we're going to go through and we're going to move all of our terms to one side. So this way we get 0 on the other. You need 0 on one side. Then we're going to do our interval testing. And so we're going to find our important numbers by figuring out where the numerator equals 0 and where the denominator equals 0. Once we've got those important numbers, then we create our number line, pick a test point in between each of those important numbers, and see if that interval works. And you also check your endpoints too. So I want to kind of go into the reasoning of this, just so it kind of makes more sense. So your important numbers for interval testing come from your x-intercepts, where your numerator equals 0. So your rational function, if it has an x-intercept, it can change signs through the x-intercepts. So this is where the numerator equals 0. You also can have a rational function change signs around an asymptote. So if we have a vertical asymptote here, your rational function could be negative on one side and positive on the other. And this is why we want 0. We're trying to see where the function then is positive or negative. So the important numbers come from intercepts and asymptotes. So let's do a couple different examples. We want to solve these inequalities and we want to express our solution in interval notation. So this is where it's super, super, super natural. You see this and you want to multiply by 4 minus x, but under no circumstances can we do that. These are way more complicated than wiping the fractions. Only for equations can we do that. So instead, I've got to move everything to one side, so it's definitely much easier to just add this x over to be able to get 0 on one side. Okay, so we've got 2x plus x squared divided by 4 minus x. We're going to add x to this, and we want this to be less than or equal to 0. So I'm giving myself a little bit of space because I want a rational function, so I've got to get this to a single fraction on this side. So currently this has no denominator, so I need 4 minus x in the bottom, means we need the same thing in the top. Okay, so this is really 2x plus x squared over 4 minus x. And we're going to add to that x times 4 minus x over 4 minus x. Okay. And now that they have the same denominator, we can make one giant fraction with 4 minus x in the bottom. It's really easy to mess up signs here, so I like to just say I'm taking one numerator and adding the other. You'll see in the next example why I like doing this better. And then I can distribute this x. This is plus 4x minus x squared divided by 4 minus x is less than or equal to 0. And then luckily, minus x squared and plus x squared cancel each other out. So the inequality this boils down to is 6x over 4 minus x needs to be less than or equal to 0. Okay. So I've boiled it down to a rational function, and that thing I could graph by finding the intercepts, finding our asymptotes, and then plotting that picture. And I'm trying to see basically where this rational function is negative. So the easier thing, though, I can do is we can find our important numbers. We set the numerator equal to 0, and we set the denominator equal to 0. So one important number is 0 itself. And then over here, we can just add x. And 4 is another important number for us. So when we go to do this interval testing, 0 and 4 are the two key numbers. And that really breaks this number line into 3 different intervals. Okay? And we'll worry about these endpoints in a second. Right? So what I want to do is I want to pick a number from each of these different intervals, plug it in. You can really do either one of these. This is definitely the easiest to plug it into, though. And I want to see, does this interval work? Okay. When it comes to the endpoints, 4 we can't fill in because that's what caused the denominator to equal 0. Okay. However, this one we can fill in because it's that less than or equal to symbol. Okay. If it was a strict inequality, then I wouldn't be able to fill this circle in either. Now I need to see which intervals work. So I start with interval 1. A number that falls in there is -1. So if we plug that into our inequality, that's 6 times -1 over 4 minus -1. We want this to be less than or equal to 0. That gives us -6 in the numerator, 4 plus 1 in the bottom. So this is -6/5 is less than or equal to 0. And that is a true statement, so that means interval 1 is good. Right. Moving on to interval 2, a number that falls between 0 and 4 is +1. You can pick 2 or 3 either. So plugging this in, that's 6 times 1 over 4 minus 1 is less than or equal to 0. Which is 6 over 3 is less than or equal to 0. And I really don't care what that simplifies down to because a positive number is not less than or equal to 0. So interval 2 is no good. So one final interval, something that is bigger than 4, we can plug in 5, 6, 7, whatever you want. 5 is the first natural number for me. So we plug in 5, and that gives us 6 times 5, 4 minus 5 in the bottom. So 30 over -1 is less than or equal to 0, and this one is something that makes sense. So interval 3 is good for us. So the solution to this in inequality notation would be interval 1, which is -infinity to 0, and we can equal 0. And then we start at 4. We can't equal it, though, because that's the problematic number in the bottom. And then it goes to infinity, right? So that's our first example. Let's try one more, and this one's definitely more complicated to get it to the step we need. So right now, I've got 2 fractions, on two different sides, I got to move everything to 1. So it really doesn't matter which one you subtract, but I'll go ahead and subtract the 3 over x minus 1. And I'm going to give myself some space because I have to get this to a single fraction. So this second one, to get the same denominator, we need an x minus 2 in the bottom, which means we need it in the top. For the first one, I need to multiply it by x minus 1, which means we do exactly the same thing in the top. Okay. And now at this point, I can skip a little bit of steps. My common denominator is x minus 1 times x minus 2, and we have 0 on this side. This is where it's really important to not just start distributing stuff out. I need to multiply these two numerators, and I need to subtract the multiplication of these two. So I like writing it out as it's this 1 minus this other. Okay? Because it's very easy to just start distributing this and say it's 3x minus 6, but you need to subtract that entire thing. So this minus sign is going to have to distribute to both pieces. So this is why it's really easy to make a small sign error, and unfortunately that can make the problem almost impossible for you to do, right? So just be super, super, super cautious. From here though, now I can distribute those numbers. So that's 4x minus 4. And distributing that negative 3 gives us negative 3x plus 6. And then this bottom you can leave completely factored. It's no reason to multiply this out because you're going to have to set it equal to 0. And then through our simplification, 4x minus 3x is x. Minus 4 plus 6 gives us plus 2 in the top. And then we still have x minus 1, x minus 2. We want this to be greater than or equal to 0. So our important numbers for interval testing are going to be where the numerator equals 0, which is negative 2, and then where the denominator equals 0, which is 1 and 2. So we set up our number line, putting all of those in order, and thankfully they already are. Negative 2, 1, and 2 are the important values. So unfortunately this time we have 4 different intervals that we need to test. Okay. And then figuring out which ones to fill in. 1 and 2 were the bottom. We do have the greater than or equal to symbol. So the 1 in the numerator I can equal, which is negative 2. I can fill this one in. So again, that comes because it's greater than or equal. These are where the denominator equals 0, so I can't fill them. Now I've got lots of values that we have to pick and plug in. So from interval 2, we can pick x equals negative 3. So that gives us negative 3 plus 2 in the top. Then negative 3 minus 1, negative 3 minus 2 in the bottom. So that's negative 1 over negative 4 times negative 5, and we want that to be greater than or equal to 0. And again, I don't really care what this number is, but kind of keeping track of the minus signs. We have 1, 2, 3 minus signs being multiplied. Overall, that's a negative number. So this interval is not going to work for us. Moving on to interval 2, a number between negative 2 and 1. You could pick negative 1, but 0 is always nice to plug in. So again, I'm plugging it in back here because it's just a nicer expression to deal with. So this is 0 plus 2 over 0 minus 1 times 0 minus 2. So that gives us positive 2. And then negative 1, negative 2 in the bottom. And again, I don't care what it is. The bottom I know becomes a positive number. So a positive number times a positive number is indeed going to give us something that is greater than or equal to 0. So interval 2 does work out. 2 more intervals to test. 3 is definitely the hardest though, because I don't have a nice number between 1 and 2. So I got to pick a decimal. Let's do 1.5. So in the top, we're going to have 1.5 plus 2, and then 1.5 minus 1, 1.5 minus 2 in the bottom, and we want this to be greater than or equal to 0. So that leaves us with 3.5 in the top. 1.5 minus 1 is 0.5. And then 1.5 minus 2 is negative 0.5. And so I have one minus sign being multiplied. Unfortunately, that does not give me something greater than or equal to 0. So interval 3 is no good. Finally, we pick something from interval 4, and we can pick 3. So this gives us 3 plus 2 in the top, 3 minus 1, 3 minus 2 in the bottom. So that leaves us with 5, and then that's 2 times 1. Don't care what it is. I have all positive numbers. It is definitely positive. So interval 4 works for us. So our solution in interval notation is interval 2, which is negative 2 to 1. We can equal negative 2, but not positive 1. And then also interval 4, which is 2 to infinity. Right. So be very careful with these. I know it's seeming like there is a pattern, like it's every other one. That's not always the case though, so don't kind of fall for that trap. You have to actually test each interval. So we can definitely create problems that don't follow a pattern.